So we've done this. Let me straighten up the camera. So we did this whole thing last time with the simplification of the formulas, and today we're going to apply them in a two-step case. Okay, so this is these are the slides that were not shown on the last video, so we just go through them real quick for those who may be watching. This was the result of our density calculation, and we wanted to propagate the uncertainty. And so we had the RSDs of both the mass measurement and the volume measurement. And the thing that I wanted to show on the video that I didn't get to because this wasn't being shown was the ability to simplify these. So when you're looking at your uncertainty analysis, especially for multiplication and division, for addition and subtraction it's very easy because you're just adding the squares of the standard deviations. And so when you're adding things, you can see which one is the biggest term. When you're adding fractions, I mean, you've got to do a little bit more work. It's not too much, but a little bit more work. And so what I typically do is I just move the decimal place over to here and look at that fraction as 5 over 13, right? And so I can kind of get an idea of what the size of that fraction is. So that's 5/13, and this one is 2 parts in 25. Okay, so this is about 1/12. Okay, this is about 1/3. Okay. And so definitely our volume fraction is bigger. Our uncertainty in volume is bigger relative to the amount. And so that's the one that's harming our precision, is the volume measurement. So when you figure this into the uncertainty, we end up with a plus or minus 7.6 grams per mil. And so our result is just not very well known. And then we looked at the 50% confidence intervals and the 95% confidence intervals. And we were saying, even though this was pretty bad analysis, we could say confidently that it's not magnesium or one of those really light elements, the ones that are not very dense at all. And so we got to this example, and this is probably a more common example, is when you do a calibration, come up with a fit. You have, in this case, 5 standards. This is actually a very good calibration line. We've got 3 9s and a 4. Sometimes you'll have in your procedures a requirement on your R squared. So it'll say, you know, make up your standards, make 5 standards over this range of concentrations. And in this case, we have parts per billion cocaine. And it, you know, it may say the range must cover, say, 2 orders of magnitude or 3 orders of magnitude. And so in this case, we really are all within the hundreds. So we're just all within 1 order of magnitude, meaning they're all in the hundreds. So 2 order of magnitude would be some standards in 100 part per billion and some standards in 1,000 part per billion. So how many place values is your concentration range covering? That's what we mean by order of magnitude. Okay. If you had a calibration range of 5 orders of magnitude, that'd be crazy. But sometimes you have instruments that have that full of dynamic range. So you would have some that were down in the tens, hundreds, thousands, 10,000s, and 100,000s. That would be 5 orders of magnitude in concentration. Those are very difficult to do, but you can do that. So in this case, and some of the standards will say, you know, once you do your standards and you calibrate your line or fit it to a line, they'll have requirements on the R squared value. And they'll say you must have at least 2 9s. So it needs to be 99 point something R squared. This one's 3 9s. Sometimes, like in our carbon monoxide lab, when we do the linear regression, we fit our data, I was getting 5 9s out of that. So a physical chemist is R squared of 5 9s, or it's junk, okay? But in analytical chemistry, rarely do you ever get a calibration line that's, you know, even this good. Most of the time it's just 2 9s and a 5. Okay. And so then you go in and you analyze your unknowns, and those unknowns come in, so you run it 3 times, and you get Y values out of that. You've calibrated the signal, and you need to calculate what the concentration is. So you use this line to calculate the concentration, and you get 3 different concentration values. So you could actually take the average of those 3 concentration values and come up with a standard deviation that way. So instead of taking the average Y value and computing the average X value, You could take each individual y value, calculate each individual x value, and get a standard deviation that way. And so that's one way to do it. Another way to do it is to do what we're going to do today, and that is propagate the uncertainty from the average y value and its standard deviation over to the average x value and its standard deviation. So we want to see how we could calibrate or propagate that uncertainty through this linear fit and come up with that average value for parts per billion cocaine plus or minus the standard deviation. And so this trend line doesn't actually give us enough information to do that, because we have the linear fit. It's y equals mx plus b. M is the slope and b is the intercept. And notice I have no measurement of uncertainty on either one of those. So I have the equation for the line, but I don't have the uncertainty values. To do that, you need to do the analysis of variance, the ANOVA table. So you would take this data and you would run it through the linear regression tool that we used in PChem. So you go up to Data Analysis Tool Pack, you have to get that installed in Excel, and then you go to Data Analysis, find the regression entry, hit OK, and then you select your X values, which in this case is your concentration, and you select your Y values, which are your area counts from the GC, and then or the LC, and then you run the regression analysis. And the nice thing about this is it gives you these coefficients, which you already had from the trend line, okay, but it gives you this block here, the standard error. And so those are the uncertainties, or the standard deviations in each one of those. And so it gives you M plus or minus and B plus or minus. And so with that information, you can take the 5.9 here and put it in your equation, and you can take the 120 and put it in the equation. So now you have a more useful linear fit. You have not just M and B, but you have the uncertainties in each of those. But now that we have the uncertainties in M and the uncertainties in B, how do we get the uncertainty in Y? So that's the real question. And if we know the uncertainty in Y from 3 measurements, how do we get the uncertainty in X? So we need to propagate the uncertainty through this equation. And so if we're given a Y value plus or minus SY, we can get that from our 3 runs. So we run 3 samples, we get 3 different signals. We can take the standard deviation of those 3 signals and we have plus or minus SY. How do we find S of X? So our M is 416.6 and our SM is 5.9. So we're using those propagation of uncertainty equations, and so we need to use the terminology. We have M and S sub M. And we have B, which is 1214 area counts, and then S sub B. Now in an earlier set of notes, this area counts, it said parts per billion. That was just a copy and paste error, so it's been corrected here. So if you're confused because you have some old notes, maybe that's the issue. Okay. And then we run 3 check samples. So we put in 3 samples. It's 125 part per billion check sample. So we know the answer. We're just trying to see if we get the right answer by running it through our calibration curve. And we'll do more with this in like 3 lectures. So we would take 125 part per billion standard. We run it through our calibration line to see how good it is in producing that answer. And we get 3 area counts, 57,000, 55,000, 54,000. We take the average of those 3 and the standard deviation, and we get these values here. Now I'm keeping all those digits because, again, we're going to use those in this propagation of uncertainty, and so we won't round until the very end. And so that's our Y value, that's our S sub Y. And so we have all the information we need to propagate the uncertainty. The only thing we don't know is X and S sub X. So here's our equation, Y equals mx plus b. We solve for X, so X is Y minus b over M. That's straightforward. 55,333 minus 1214 over 416.6. Then you can check the units. They work out to give us parts per billion. And so we get 129.9 parts per billion. Now we could look at this immediately and say, well, we're a bit off. 125 is our check sample, and we got 129.9. Okay. But what's our uncertainty? Does our uncertainty contain that check value? Right? If our error bars are, 4.9 plus or minus, then we're going to contain the 125, and so we got a decent answer. But if our error bars are really narrow, then we have some bias in the system. Everybody catch that? Is our check sample value, the 125 parts per billion, within the uncertainty of our measurement? We don't know yet because we haven't calculated the uncertainty in X. So you can't just look at this and say, oh, our calibration is no good. It might be very good. We might have some uncertainty in our measurement, and 125 is within that uncertainty, and so we're good. Or we might be very precise and have a bias, and then we need to figure out what's giving us a biased result. And so this is what we need to use the propagation of uncertainty to do, is to find that S sub x. So what do we have here? We have an equation, x equals y minus b over m. And when we look at our propagation of uncertainty table, we have a row that's addition and subtraction, and we have a row that's multiplication and division. And this problem has both in it. So it's just a two-step problem. Once again, it's not hard, it's just tedious. You just got to work your way through each individual step. Now, if you're going to calculate this, you've got those numbers, you're going to use a certain order of operations. You're going to take the y minus b first, and then you're going to divide by m. You do the same thing with the propagation of uncertainty. So you calculate the uncertainty in the numerator first, and then you calculate the uncertainty from the fraction. That's a step that people don't understand. They look at this and they go, what do I do first? Well, how would you calculate it? You would calculate the numerator first, and then you would take the division. And so you do the uncertainty for the numerator, and then you do the uncertainty for the fraction. Okay, so you follow the same order of operations. So in this case, we've got a subtraction, and then we've got a division. So let's do the subtraction first. So our numerator, so I'm just going to make up a term. I mean, I could give it a constant. I could say k or something like that. I'll just call it numerator. Numerator y minus b. And so that value is 54,119 counts. We have to know that value because we're going to take the relative standard deviation of that numerator value. So we have to calculate the numerator and hold it. So we've calculated the numerator, and we need the uncertainty in the numerator. Okay, so this numerator is an addition and subtraction piece. So the equation that we would use is that the variance of the numerator is equal to the sum of the variance of y and the variance of b. Now the variance is the standard deviation squared. So we take the uncertainty in y and square it, the uncertainty in b and square it, add those together. Okay, and that would be the square of the uncertainty in the numerator. If we want the uncertainty in the numerator, we just take the square root. So that's what we have. The uncertainty in the numerator is the square root of the uncertainty of each of those pieces squared. And we have all of those terms up there on the left. So we take the uncertainty in y, which was 1528, and the uncertainty in b, which is 120. We square those, add them together, and take the square root. So our numerator uncertainty is 1,532 area counts. Okay. So now we know the numerator and S numerator. And now we can use the relative standard deviations to do the fraction uncertainty. Let me pause here. Is there anything that you need clarification on? All right, seeing nothing, let's move on. So now we need to understand the uncertainty in X. Since it's division, we have the relative standard deviation of the numerator and the relative standard deviation of M. You see that? It makes sense now, doesn't it? The numerator is its own piece. And so then we just take this S numerator divided by numerator, and then SM from our table over there divided by M. We square each of those, add them, take the square root, and then multiply by X to get the standard deviation of X. So here's all the numbers. You can find them in the table and see where they came from. And so then you put in all those numbers and you end up with 4.1 parts per billion. So 129.9 plus or minus 4.1 parts per billion. It doesn't quite capture our 125. So we do have a bit of a bias. Okay. We're coming in with a little bit of a high calculation on our standard. So this is the full calculation for propagating through a linear equation. Any questions on this? Where would you get tripped up? Because I know that y'all had some difficulty with this in the PChem lab, and some, when I asked the TAs, they were like, yeah, some people didn't do it, or some people did it and they weren't sure how they did it, because it's hard to see, all of the work done for the propagation of uncertainty if you don't explicitly show your work. So where would you get tripped up? What I'm trying to do is try to get you to think through this mentally. If you were just given a blank sheet of paper, where would you get tripped? It looks so easy when it's all revealed in PowerPoint. And you're like, yeah, that makes perfect sense. How would I ever mess that up? Yes?
Like, this part makes sense, but I think like calculating the ANOVA, I know I had trouble with that.
Okay, sure. Yeah, and so that's a critical piece of it. So, no, I have I know I have a video on that, but I think it's in the PChem folders, Let me make a note that, that I could put up a short video on the ANOVA step, because that's really critical. You need to know the uncertainties in M and the uncertainty in B. Now for the exam, you'll be given those. So I'll give you the equation for the line, like up in the red box. So if you've given that equation with the plus or minus for each of those, you should be able to do this. But on your own, I want you to know how to do it in Excel. So let's see. I'll tell you what. Would you just pull your phone out and shoot me an email and just say, make a short video for the ANOVA? That'd be great. I appreciate that. And so this is one way to report our data. This is not a confidence interval, really. Well, it's a plus or minus 1 standard deviation confidence interval, which is really like a 63% confidence interval. If you just use plus or minus 1 standard deviation, you're capturing about 63% of the Gaussian curve. So it's not a great confidence interval. And so a lot of times, we'll talk about what confidence intervals are here in a second. But notice at least, there's if that's, say, 60%, then we have a 20% chance of being too high and a 20% chance of being too low. So we missed our check sample value of 125 parts per billion, but with the plus or minus, our 60% confidence interval, that's not that surprising. If we put in, say, 95% confidence, we would definitely capture that 125. So our bias is not too big. So let's look at some basic statistic terms from last class. This is just a real short one. 651,352. Two more.
It won't let me enter your nickname.
That's weird. I see it.
And then every time it's like, hold on, don't forget to enter your nickname. I'm like, that's what I'm trying to do, but it won't. Come on, I'm gonna start it.
Okay. Let's see if you can get back in before somebody else gets dropped. Everybody keep messing with your phone so it doesn't go to sleep. That's weird. What's going on?
It's not letting me.
I'm watching the whole thing. And then people are getting dropped out, yeah. It's okay. It's not like you're not gonna lose any points.
Okay.
So, all right.
I mean, I'm trying.
Yeah, I know. I saw you trying. Yeah. So it's just 4 quick questions, and mainly just to kind of keep people going. So why use the sample standard deviation instead of the population sigma for a small data set? You can pick your favorite answer.
You're in screen.
Oh, what happened?
I don't know.
It's that row. There's something wrong. Y'all are right below the hot spot. Yes. So a couple of answers here. S is larger than sigma, which also means it's a more conservative estimate. And so that, again, when we use conservative in this, this means we're being safe, okay? It doesn't mean that we're political, okay? Which estimate of uncertainty is largest relative to the mean? So we're looking at 4 different situations. Which estimate of uncertainty is largest relative to the mean? Yay, very good. Okay, so this these other options, 560 parts per million, that's really small. It's 560 times 10 to the minus 6. So, or 0.56 times 10 to the minus 3, or 0.056 times 10 to the minus 2. And these others were at 10 to the minus 2. So 75 times 10 to the minus 2, 35 times 10 to the minus 2, or 0.056 times 10 to the minus 2. Did you get in?
Yeah, let me
Will
in
it
now.
let you add though once we started?
I don't know, but it says on
All right,
it,
we'll see.
so-
All right, 2 new players. Yeah, no, it didn't say that. Let's see.
You're in, but you're not sure.
Yeah, what's it say? What's it show?
It's going.
Oh, very good.
It's
Okay.
going. Okay.
So the needle is exactly between 2 tick marks, labeled 7 and 8. What do you write down? Yay. Good job, folks. When the precision of multiple groups is being reported, do you use the which? There's a whole lot of standard deviations. It's like there's no standard. All right. That's good. So you use that pooled standard deviation, which again is really the weighted average of all of the variances. So if you remember variance, that's S squared. So that's a statistical term that's super useful. So get that into your mindset. I know we use standard deviation a lot in chemistry. We very rarely use the word variance, but variance is really helpful because a lot of times it's the S squareds that are added. Right, and so in addition to subtraction and also in other analyses and statistics, the variances are the things that add up to 100 or add up to what have you, So, very good. They've added this little animation. It's kind of like the end of Mario Kart, which I absolutely love Mario Kart. Greatest game ever. Dun dun dun! Yay, Cal 56. What's that?
I think in all of PChem and this class, that's my first time.
Alright, props. That's fun. I was worried that the Kahoot would be too, juvenile, because all the video, the B-roll is little kids, like 7th graders, or maybe 5th graders getting all excited. And when I first did it, the students in PChem, like this one girl, she was like, tense, and she was like, yeah, and I was like, okay, so it's not just 7th graders. There's a little bit of competition in there, which is fun, and everybody likes a little bit of competition, And it also was really helpful to me because I thought, all right, it's there to reinforce what I just said in lecture, and that helps everybody. But I didn't really realize that it would push the people who, say, already have it to try to get it quickly and correct, and so it's sort of, it works at both ends. So it's a commercial for Kahoot. Break the fourth wall. Okay, so we have the nature of random errors. What's going on with the standard deviation is we have a real, the result. You put your sample in the machine and out comes a number, and it's almost impossible for that to be unperturbed, on its way from the analyzer, light, scattering, detector voltage fluctuations, all these different things will wiggle that number. Everybody looked at an Olympic swimming pool or just a swimming competition pool where you see that line down the middle on a nice calm, before anybody gets in, that line is crisp, okay? But once it starts to get, the water starts to get wavy, you see that line kind of wiggling all over the place. Well, we're collecting our data sort of under that wavy water. So our answer's doing this all the time. We can't see those fluctuations, but we're trying to collect data underwater, if you will. And the number that we're trying to get is real wavy. Okay? And it wiggles back and forth. And so if you just had, what first fluctuation, if the waves were just totally side to side, that line would move predictably left and right. And you would see maybe a leftmost and a rightmost, and that would be just one fluctuation. But then maybe you have a couple of waves, periods going in there, and now you have 3 possible answers that are common. If you extend this to a near infinite number of variations, and you end up with this Gaussian curve. Okay, and you can show just mathematically, starting with this and adding in all these fluctuations, that it will converge to a Gaussian. Where have you seen this pattern too? 1 1 1 2 1 1 3 3 1 1 4 6 4 1. Anybody? Pascal's triangle, and you've seen it in organic. Why did you see this in organic? You're like, wait, we didn't do any math in organic. Anybody? NMR splitting patterns. Yeah, so you got this proton up, down, splits me with 2 ways, and then this one splits those, and now I've got 3 possibilities, and I've got 2 ways to the middle one, so it's twice as big. And so again, the coupling number of equivalent nuclei will give you these splitting patterns. And if you extend this to an infinite number of splittings, you get back to a single peak that's just really broad. Okay. Or if you don't resolve the hyperfine splitting, you have a Gaussian peak. But if you can resolve it, it splits into these individual fluctuations. Okay. And also there may be environmental insults that if you could, quote, resolve them, you would get 2 answers. Like if you're running a Spec 20 and our power grid in the building, let's say it's not very good, and you measure one measurement and you get a value and you write it down, and then you put another measurement in there and somebody gets in the elevator, and it draws the building down a certain amount because it's a certain pump and so on, and your bulb dims. Your sample looks like it's absorbing a lot more light, so your absorbance goes up. And you could maybe resolve with and without the elevator. And so this is a real common thing is air conditioners come on, elevators start to move. There's lots of things that can happen. It's early in the morning, and then the whole dorm, everybody's got a hairdryer going, and the whole city is being drawn down. But anyway, infinite number of random fluctuations leads to this normal distribution, this Gaussian distribution. And we have some confidence that the true value is somewhere inside this peak. So that's what we're trying to get to. We start with this peak. This is what we measure. And if we measure like 3 values, we get this one, and this one. We take those 3 values and we find an average, x bar, and a standard deviation. Well, I should say S. Okay. And the distance from the middle, the mean, to the inflection point on that curve. Do you know what I mean by inflection point? Look at the curvature of this curve. It's curving down, and then it's curving up. And where it stops curving, that's the inflection point. So it goes from curving down to curving up, and so it's not the full width at half maximum. A lot of people make that mistake and think that the standard deviation, or sigma, is the full width at half maximum. It's not. It's the distance from the center point of that Gaussian to the inflection point. There's an equation that you can convert one to the other. And so what we'll do is we think of that Gaussian curve. If that's the integral over all the possibilities, then dealing with probabilities, we want that integral over all space to be 1. Just kind of like we did with our wave function squared. That was a probability distribution. So is this. This is a distribution of our data. And we would integrate that, and we would set that area equals to 1. So we might have a normalization constant. You don't have to do any of that, but that's what you would do to get this area equal to 1. You would normalize it. And then you would have your mean plus or minus some area, and that plus or minus would capture some fraction of the area under that curve. And so even if you have a tall, skinny peak, the area under that curve is 1. If you have a really broad and low peak, again, the area is still equal to 1 because we're trying to capture all the possible results. And then you take that mean plus or minus a certain fraction of your standard deviation, and you're going to get your confidence interval. So the integral from minus 1 sigma to plus 1 sigma is resulting in 0.683. So that's, I was saying 60% is really 68%. So plus or minus 1 sigma captures 68% of the area under that Gaussian. So it's going to give you a 68% probability of capturing that true value if the thing wasn't biased left or right. You know, those fluctuations, the Pascal's triangle, we were right underneath the true value. Okay? We only measured 3 samples, so we might be off a little bit. And so we're saying that true value has a 68% chance of being plus or minus 1 sigma, which we're trying to find that true value. 95.4 would be the integral from minus 2 to plus 2. And then 99.7 would be minus 3 to plus 3. So that's pretty good. If we wanted 99.7% confidence, we would do 3 sigma. Pretty broad range of concentrations. So that 129.9, if we multiplied that 4.1 times 3, it'd be 12. Okay, so we can say it's 129.9 plus or minus 12 parts per billion. And that definitely contains the 125. So, and we would be 99.7% confident that it would capture the value we thought it was, and we did. Okay. And so that's what we're doing with those confidence intervals. They're derived from sampling statistics, and it's the likelihood of containing the true value of an unknown quantity. So a 95% confidence interval, 19 out of 20, that's 5% missing, 19 out of 20 times that sample population will produce confidence intervals that contain that population mean. And so we derive these values from that standard deviation and the Gaussian distribution. So let's think about it though. Even if we wanted 99% confidence, plus or minus 3 sigma, or close to 3 sigma, in some situations that's not very good. Okay, but 99, I mean that's great. Wouldn't it be frustrating if you turned in a paper and you got a 99.7 and I said that stinks? You know, that's pretty harsh. But you know, think about this: we don't want 20,000 lost articles of mail per hour, or unsafe drinking water for 15 minutes a day, or 5,000 incorrect surgeries per week. You go in for knee surgery and they replace your hip. You did what? Yeah, that's funny sometimes that like my parents and their friends all have artificial knees now. You know, they go in right before the pre-surgery and the pre-operation, and they're getting, you know, the IV and all that stuff, and the doctor comes in, talks to them, and while they're still awake, says, "Now it's your right knee," and they say, "Yes," and so he writes this one in Sharpie on the skin. I mean, why not, right? It's just the risk of doing the wrong knee is so great. It's way greater than writing on your skin with a Sharpie. I'm sure it's some special Sharpie that can be wiped off, but still, a little alcohol will get it off. But yeah, do this one, you know, and they run on the other one. Not this one. Because they're in there just replacing knees all day, you know, and they get in there and start cutting. Or landings at airports, really important. You know, we don't want to run off the end of the runway. We don't want to hit the swamp right before the runway. So that's not cool. And 200,000 incorrectly filled prescriptions per year. Oof. Yeah. Yeah, I know. That's right. So, or no electricity for 7 hours a month. We get that anyway in Huntsville with the trees. It's gotten better, you know. We live in Westridge, and so the trees fall on the power lines. Well, they did something. They rerouted some of our lines and cut them back so we don't lose power nearly as much. But my wife's a believer in the jinx. You know what I'm talking about, the jinx? You know, you say, "Oh, we'll be fine. Nothing's going to happen." And she's like, "Oh, don't say that, because now something's going to happen." And so we were sitting around the house, and there was a windstorm coming in, and she's over at the computer. We have our computers in the family room. We're all just hanging out, and she's typing away. And she says, "Wow, with all this wind, it's amazing we haven't lost power." And in the dark, you hear, "The jinx is real." From that point on, we were like, "Yeah, it is totally real." I mean, it was the second she finished that statement. It was great. Of course, with 16,000 murders in the U.S., this was in 2008, 99% confidence would yield 162 wrongful convictions. That's crummy. Murder. Yeah. What's that? Oh, yeah. So that's why we take at least three methods. We hope each of those methods works at 99% confidence. Because what is 0.01 times 0.01 times 0.01? So 0.01 times 0.01 moves the decimal place 2 more places, and then moves it 2 more places. Okay, that's now 1 part per million. So if we have 3 99% confidence operations, you know, a check sample, a chromatogram, and then like a mass spec, and each one of those is operating at 99% confidence, there's a 1 part per million chance that something's going to get through all 3 of those filters. We're going to catch it on one of them. So we don't just do one analysis and say, "Yeah, but we're working at 99% confidence. Who could ask any better?" It's like, well, society asks for better. You know, we're not going to just base it on one instrument working at 99% confidence. So there's a move called Six Sigma. It's a quality organization that attempts to design quality into a process. This is big in the automotive industry. I don't know, you weren't around in the 80s. Automobiles were pretty junky. Okay, in the 70s we had this OPEC oil crisis. It looked like we were, you know, really needed to up our game in terms of fuel efficiency. And so the best way to make fuel efficient cars was to make them lighter. Okay, they didn't really change the engines or anything at that time. That took a longer design life to change the engines. And so the simplest thing was just to make them smaller and lighter, and they were junky. And so late 80s, 90s, 2000s, the quality caught up. And so these Six Sigma organizations worked their way into Toyota and Ford and Chevy, GM, all these different major automobile companies implemented this quality program where they try to design it into the process. It's pretty amazing. Now, if you ever find yourself in San Antonio, go tour the Toyota truck factory. Okay, you can just sign up online for a tour, and you will see Six Sigma in action. It's just amazing. They put you on a little, little train of. Anyway, everybody sits there, and you have these ear protection, earmuffs on that have a little speaker in them, and the person on the front is telling you what you're looking at. And it's really cool. So everybody's working on the production line, and these little line-following robots, just like the Lego NXT, comes up with all their parts. And then they turn around and grab the parts or whatever, and when the thing's logging how much they're using, and when it's empty, the little cart just goes off on its own, and another little robotic cart shows up. It's so cool. Yeah, it's just like I don't know. There's like the droid factory, in Star Wars. I'm a big Star Wars fan. Not quite that cool, but you feel that way. Lots of things. Now, what is Six Sigma though? So Six Sigma is the variability in your process is your sigma, and you also have customer specifications. Now in forensic science, we have customer expectations, right? We don't want you to say that something's cocaine if it's not, okay? And so you're gonna have a detection limit, you're gonna have a limit of quantitation, and you don't want your uncertainty to be so broad that you're going to bump that limit of quantitation and say, oh, this wasn't cocaine when it was, or to have pretty much a blank signal, but to have an uncertainty that's big enough to say it is when it isn't, right? So it can go both ways. And so you want your sigma, your Six Sigma line, if you say, if I'm gonna say this is cocaine, I want my limit of quantitation to be high enough so that there's 6 standard deviations before I'm gonna say it's not, okay? And what that gets you is that you'll be only 4.3 false negatives per million opportunities. And that's pretty good. Now, forensic labs are probably in the process of implementing something like this. I know this because of my time in industry, we were implementing it. And so if it's not called Six Sigma, it'll be something like this. You have your lower specification on the left, your upper specification on the right, and you want to be 6 sigmas away from that. Now, if you've got a really wide distribution in your data, then you've really got to be far from those specifications. But if your data is very, very precise, then you can move up. If you have like just a paper thin uncertainty, then you might be here for your upper spec and still be 6 sigmas away, and you might be here for your lower spec and still be 6 sigmas away. And so your precision in the process really helps your range of values. And if you've got a really ugly process, a really fat curve, then you've got to be here for your upper specification and here for your lower specification. And so your operating range is pretty narrow because your distribution is so wide. So you want your analysis to be super tight. Put the same sample in and I get the same answer out. And then I can operate in a wide range because I don't have any uncertainty. I'm not going to trigger the false negative or the false positive. And so that's the main part. Let's go through some of the supplementary examples. These are just some propagation of uncertainty examples. Here's a serial dilution one. And so we have a 1 mil standard containing 1 milligram per liter, and it was used to prepare a 1,000 parts per billion stock solution. And a syringe was used to transfer 250 microliters, plus or minus 0.5%, to a 250 mil volumetric flask, and plus or minus 0.03%. Now, one thing I want to point out is there's a couple of different ways of reporting uncertainty in this example. Okay. And that's just life. You're gonna have a mixed bag of things that you get. We haven't really talked about this one, but what's this parenthesis mean? What is going on here? This is a reporting of the uncertainty. And so that parenthesis is telling you the place value and the magnitude of your uncertainty. So this is saying that your uncertainty S is equal to 0.01 milligrams per mil. Notice I have 1.00 and then the parenthesis begins, and that's telling me that the place value right next to the parenthesis is where this number belongs in terms of my uncertainty. You could also have two values of uncertainty. If I said 1.0015 milligrams per milliliter, I'm given two values of uncertainty, and that just means it replaces the previous two place values. And so then S would be 0.15 milligrams per mil. Okay? So using those parentheses, that's a real compact way to write uncertainties. And you'll see that in the practice exam, but you'll see that also if you go to the NIST website and look at the physical constants for the universe. You know, you'll see Planck's constant written out, 6.626, and it goes on and on and on. But eventually you see a parenthesis and a couple of numbers, and they're telling you where the uncertainty is in that constant. Okay? Or Avogadro's number. It's got like eight significant figures. But then you'll see the parenthesis, and it's telling you the place value for those uncertainties. And they typically use two values of uncertainty. So it's just telling you when you're given two values of uncertainty, it replaces the previous two place values. If you're just given one, like on the screen, then it just replaces the previous one place value. Notice I'm saying place value, so whatever, you know, if it's hundredths or thousandths or whatever, it's just wherever that place value is. For like Avogadro's number, it's down in the 6th or 7th decimal place. And it was used to prepare a 1,000 parts per billion stock solution, and we don't know the uncertainty in the stock solution. That's what we're going to try to figure out. Okay. The syringe was used to transfer 250 microliters, plus or minus 0.5%. Now we've got a percent here. So percent is a coefficient of variation. So that's actually a fraction. That's the uncertainty divided by the value. And so we've got to figure out what S is for the syringe, and then the same thing with the 250 mil volumetric. It's plus or minus 0.03%, so also a coefficient of variation. So here we've got the commercial standard and that 0.01, so there we know the uncertainty there, no problem. We could calculate the RSD and the CV just for grin. For this one, we're given the CV, so this 0.5 goes right here. And so then the RSD is 0.5 over 100%, or 0.005. And that's equal to sigma over 250 microliters. And so we need to take that 0.005 and multiply by the 250 microliters to get our uncertainty. So this is our sigma for the syringe, 1.25 microliters. So that's why I was saying you need to be able to go back and forth from CV to sigma, and forwards and backwards. That needs to be just second nature. So go through this example, make sure you understand every one of these. Same thing for this one. CV is 0.03%. That means the RSD is 0.0003. That's equal to the sigma divided by 250 milliliters. And so you need to solve for sigma. So it's 0.0003 times 250 mils, or 0.075 mils. So that's the uncertainty for the volumetric flask. And so what we want to know is we've got now a stock solution. What's our uncertainty in the stock solution? We know it's 1,000 parts per billion stock solution, but it would be nice to know if it's very precise or not. And so then we'll do that on the next page. So it's a simple dilution. M1 V1 equals M2 V2, so we can rearrange and solve for M2. So the V1 was 0.25 milliliters, the volumetric was 250 milliliters, and then the initial concentration was 1 milligram per mil. And so we wanted to make sure that it was 1,000 parts per billion. So where do we get that? We get 0.001 milligrams per milliliters, and then this right here is something that is a mystery. It's buried in these calculations. So going from milligrams per milliliter to parts per billion is a mass percent. Okay, it's a mass fraction. It's grams of standard per grams of solution. But where did we get out of milligrams per milliliter and into masses? So I've got 1 mil equals 1 gram. What's going on with that? This is probably the thing that screws a lot of people up because they don't know how to work with the units on dilutions. This is also an assumption that doesn't work for something like acetonitrile or isopropyl alcohol. You know, if you're making up your standards in IPA or acetonitrile for liquid chromatography, this will catch you. Does 1 gram per mil mean anything to somebody?
Like the density.
Yeah, that's the density of water. It's a buried assumption in here. Going from milligrams per milliliter, that's the same as, what does it say? It's the same as a part per million. And so, you know, milligrams per milliliter is 1 part per million if you're dealing with water, okay? But if you're dealing with acetonitrile, you need to put the actual density of acetonitrile in there. You wouldn't use the density of water, okay? What about the density, what about the mass of the solute? Well, most of these are very dilute, and so we just assume that the mass of the solution is the mass of whatever the pure solvent is. That's another assumption that can fail. But that's what's going on here. So this is the density of water right here. I love this touchpad. I can write in cursive. Okay, so anyway, we have, so this is that fraction that comes out. Now, I put grams of standard per grams of solution. I mean, it's sort of, I get that fraction, all my units have canceled, but that is what's going on. We've got milligrams of my standard and the grams of solution are in there. And so the grams have canceled, and we multiply that. This is our number. It's a very small number. We could multiply that by 10 to the 6th parts per million and have 1 ppm. Or since we're going to be making our dilutions from there on, we'll start with 1,000 parts per billion and make up our dilution solutions for our calibration line. And so that's typically calculated as 1,000 parts per billion. You cut it in half, you have 500 parts per billion. Cut that in half, 250 parts per billion. So we start with 1,000 as our most concentrated stock solution, and then we work our way down by dilution and make up our calibration line. So we'll go ahead and type, multiply by 10 to the 9th parts per billion, and we get 1,000 parts per billion. So that's our stock solution calculation, and that just uses the 3 values we were given. We had our standard, we had our syringe, and we had a volumetric flask. So at that point, it's really just like a freshman calculation or a quant calculation. It's the uncertainty that's added new. So now propagating the uncertainty for these, we have 3 things multiplied and divided. And so we're going to have 3 RSDs squared, added up, take the square root, and multiply by 1,000 parts per billion. So you should be comfortable with this one. It's just a one-step type calculation because we have all multiplication and division. So we have the RSD for A, the RSD for B, and the RSD for C, all squared, added, square root, multiplied by Y, which is our parts per billion stock solution. And so here we have it. This is the standard RSD. This is the, which one is this? This is the syringe RSD, and this is the volumetric flask RSD. And so then you add all those, multiply by 1,000 parts per billion, and this is our uncertainty in our stock solution. So our stock solution is 1,000 plus or minus 11 parts per billion. It's not that bad, actually. It's a plus or minus 1%. If you can get your stock solutions to be less than plus or minus 5%, then you're okay. All right? It's better to be better than that, but if it's worse than 5%, then you probably need to remake your stock solution. And if this were worse than that, which one would be the limiting factor? So let's look at our 3 RSDs. Which is the worst one? So quickly looking at this one, we have 1 in 100. Everybody see that? 1 part per 100. So that's 1/100th or 0.01. Let's forget the 2.25 and just look at it. That's 1 in 250. So where's the decimal place? This is 1 here and 250 with a decimal place there. So 1 in 250 is smaller than 1 in 100. Okay, so far this is the worst one. And then this one is 0.08 in 250. That is really small. So this one's not even giving us any uncertainty at all. And that's what you would expect from your volumetric flask. Right? The syringe is next, but this initial stock solution, the initial sample or aliquot standard is pretty crummy. So our standard that we bought was 1%. It's nice that whatever we did with it didn't add to the uncertainty. But we're limited by that standard. If we could buy a standard that was better than 1%, then our stock solution would be better than 1%. And that's kind of nice. You can look at it and say, it wasn't me. It's what I got out of the catalog. Okay. So if you find a catalog that has better standards, then you'll have a better stock solution. But isn't that cool? You can just look at it and say, okay, what did I do to the process? Nothing. My graduated still. My volumetric flask was good. I was predicting it would be the syringe. Because measuring a syringe and looking at the tick marks and everything, that's really where a bias can come from. You measure it, but there's like some dead volume in there, or the needle was empty, or the needle was full, and so you put it in, and you put in a little less or a little more than you thought. And so then your whole stock solution is off, either high or low. Here's another one, reading a burette. Did you know reading a burette, you're actually taking 2 readings? Because when you fill the burette, you're filling it, say, to 0, and that's a reading. And then when you measure, you're taking a second reading. And so there's a subtraction there. So even though the tick marks, maybe half a tick mark, the tick marks are at 0.1 mil, and you can estimate to half a tick mark, so that's 0.05. You say, well, my precision is 0.05, but it's really not, because every time you take a measurement, it's 2 readings. So 0.05 squared plus 0.05 squared, take the square root, is 0.07 mils. So that's the true uncertainty of a burette that's marked at 0.1 mils. And since this is subtraction, that's how you do the uncertainty. And then here's a log example. So you've got a pH probe, you got 0.1 mils plus or minus 0.005 mils HCl. Can I get you to close the door? So since HCl is a strong acid, it's 100% dissociated, so our concentration is 0.1 moles per liter. And what's the uncertainty in pH? So Y equals minus log of A. So that's pretty easy. It's a pH of 1, but what's the uncertainty in pH? So this is from those formulas. It's 1 over the natural log of 10 and times the relative standard deviation. And so it's going to be 0.022. So that's pretty good. Most of our pH probes are not that precise, but this is at least the mathematical precision of what the pH probe reading would be. So 2%. And so here we have a pH pen that's measuring the pH plus or minus 0.02. What's our uncertainty in concentration? So doing this backwards, it's an antilog situation. Y equals 10 to the A. And so A is minus 1, so it's 0.1 concentration. And then here's the uncertainty. This is kind of a weird one. You've got Y times the natural log of 10 times the uncertainty, absolute value there, the uncertainty. And so we end up with 0.0046. So there's our hydronium ion concentration, and here's our uncertainty. Okay, so about 4.6%. So not too bad. So, some final comments. We like to have precision, precise data, but we can have bias. We can be off to the side, high, low, etc. We'd really like good accuracy and good precision. A lot of times people will say that they have good accuracy, they got the right answer, but their precision was really wide, okay? So they got a really broad peak, but it just happened to be over the true value. But really, if your precision is bad, you're gonna have a hard time convincing somebody that your accuracy is good. Okay, so this example on the right, it looks like the darts are kind of centered around the red dot, but if your precision is bad, you can't claim good accuracy because you're just not reliable. You give me the different answer every time. I give you the same sample and you keep giving me a different answer. I don't care if the average is giving you the right answer, but you need to tighten up your error bars before I'll trust your data. Here's just some examples of some tools called Minitab. Yeah, that's a good thing to introduce. So how many people have used a statistics package in your undergraduate research, like SPSS or any of those? Anybody have any experience with? Okay, so if you do, you can use one of those. But if you don't have any experience with a statistical package, I prefer Minitab. That's the one that I grew up on. When I went to industry, they taught me that. And so this is, you can go to minitab.com. I don't know why they call it Minitab. That's just the name of software. And you get a 30-day free trial, which will certainly get us through the first exam. Okay, and I think it's optional. Okay, but I think it's worth it. If you have a computer that you have admin rights to. I mean, if you're working on the computer labs here, they have some limited seats. If you really want to use it on a computer here, I think I have it on the laptops in the laptop cart, so I might get you one. But if you have a laptop or a computer at home, you can go to minitab.com and you can get a 30-day free trial, and you can produce plots like this. Now, I'm big on Excel. I taught you how to do all this in Excel. But like I said just the other day, learning the stat functions on your calculator is worth it. Type in 5 data points and hit average, hit standard deviation. You don't have to do the table. You don't have to do the columns of squared, deviations, and all that stuff. Yes, you can do it by hand, but it's good to use the tools. You can do it in Excel by hand, but this is the corresponding tools, like learning the stat functions on your calculator. This is a program made for statistics. So if I took this data, and this was 24 images of contact angles, and students analyzed those, and the contact angle is defined as this angle right here. So this angle with the base plate and that, so it's this angle right there, theta. We had some coupons, some metal parts that we were cleaning, and we put water drops on them. We took 24 different pictures of 24 different water drops and had the students analyze the angles of those water drops. Now, you can do the standard deviation by hand, right? But for 25 data points, that's kind of a pain, okay? In Minitab, you just have a column of those 25 measurements, and you say, menu, graphical summary of statistics, go. Tell it what column, and it does all of this for you. So you get up here, you get the mean, the standard deviation, the variance. You get some skewness and kurtosis, which we will analyze later. It tells you the quartiles. It tells you the confidence intervals for the mean. That's pretty cool. So it's calculating the 95% confidence intervals. It gives you this histogram of your data. So all 25 measurements are underneath this bar graph, and it gives you this Gaussian distribution curve. It gives you the mean and the error bars, or the confidence interval for that mean. It's written also down here with numbers. What's cool about this too is it gives you the median, so the expected value, if the data is skewed to the right or the left, and And so again, we'll talk about what skew means, and then this is the uncertainty on the median. So that would be the confidence interval for the median. And it's just, 3 clicks, and you get all of that information. So it's definitely worth exploring Minitab. So this was our parts, then we cleaned the parts, and oh no, we got it dirty. We put a lot of grease on there, and the contact angle is hydrophobic grease, and this is water, so the water beat it up, and the contact angle increased. And so you could see bumps of grease on there. And so the angles were kind of all over the place. You see how we've got some, spread in our data. And then we took a chem wipe and wiped it clean. So it looked like a clean part. But the contact angle with water is going to tell us whether it's really clean or not. It's not clean. It looks clean, it's just smooth. So we wiped all that grease off, but you could still see the contact angle was large. And so it meant there was a hydrophobic film over that metal oxide. But look how narrow the data is. So again, the mean didn't shift, but the standard deviation got very small. Also, again, 16 values on this measurement. And then we put it in an ultrasonic tank and cleaned it with ultrasound. The contact angle shrunk down, and now we have a clean part. So the grease has been removed, and the water is now wetting the oxide layer. The angle of that drop is under 60 degrees. So it's a pretty flat drop, and this is cleaned. But I just really want to show you this as an example of using Minitab. We didn't have to build any formulas or anything in Excel. We just had our data, and we just analyzed it using these menu functions. And this is called the graphical summary of statistics. And you get all of this information. We'll get into what skewness and kurtosis is later, and the different quartiles and everything. But I think it's worth going and taking advantage of their free trial. I asked somebody on a statistics blog, because they were kind of trashing Minitab, and I said, why are you hating on this? Because I found it very easy to use. And they said, well, yeah, it is for those people who just want canned analyses, but if you want to write your own analyses, because you have different kinds of data and so on, then it's not very powerful. Well, I don't want to write my own statistical analysis. I just want to use the canned statistical analysis. And so, yes, for those who just, don't want to major in statistics, but just want to analyze their data, Minitab's the way to go. So there's a commercial for Minitab. So we'll see you next time.